We'd like to come back to the question of identical particles. So I remind you that even before the formalism of quantum physics was discovered, the question of identical particles was raised by Bose and Einstein on one side, by Fermi, Pauli, Fermi, and Dirac on the other side. The question was, how do you count the microscopic state corresponding to a given state of an ensemble of particles? How do you compute the entropy of the system when the particle cannot be distinguished? And this led, of course, to Bose-Einstein condensation, to the exclusion principle, and so on. Now, when quantum physics emerged from mathematical formalism, it became the issue of identity of particles became also very important. It was understood why there is a fundamental impossibility to distinguish particles. In classical physics, you can always assume, even if it's practically impossible, that you follow the trajectories of particles and you give a name of particles, you number them, and you have particle 1 at my left, particle 2 at right, and they interact, and you can keep following them. But in quantum physics, if you have a wave packet, once the particles have interacted and the wave packets have merged, there is no way after the collision to decide which is which. So there is an impossibility, even in principle, to label the particles by numbers. And so you have to find a way to solve this problem, which is a very important issue. It has to do with what is called the exchange degeneracy of the quantum states. And I show you here a very simple example. Suppose that you want to describe the collision, head-on collision of two identical particles, which go towards each other. One particle has a momentum pi, the other one the momentum minus pi. How will you write that? What would be the initial state of your system? Will it be pi minus pi or minus pi pi? That is, if you label the particles, you have two possibilities. And according also to the fact that the superposition principle holds in quantum physics, any linear superposition of the two would also be a possibility. But if you have this kind of ambiguity in the initial state of the system, this ambiguity will have consequences for the predictions. Depending upon the choice you take to start with, you will have different predictions for result of experiment, and this is not acceptable. You should have only one possible set of predictions once you know the initial state of the system. On the next slide, I just present you the problem on a very simple example, and I will let you do the calculation. I want just to show you what kind of problem we have. Suppose that you are given two spins, and you know that one spin is up and the other down, but you don't know which. And you know that the probabilities to have the first spin up and the other down is 50%, and the other one 50%. So you can write this in the way I have written on the board. It's +1 plus -1, but you have an ambiguity, you have a choice. You can choose the phase of the second term of the superposition. Any phase alpha that you put here will have the same, will correspond to the same problem. Two spins, one up, the other down, or like that with equal probabilities. But this ambiguity in the choice of alpha will lead to problems. For instance, if I ask you to compute the expectation value, the mean value of sigma 1 of the total spin squared, sigma 1 plus sigma 2 squared, I let you do the calculation. You will find that the expectation value will be equal to 4 times 1 plus cosine alpha. And 1 plus cosine alpha can vary, of course, between 0 and 2, which means that this result can vary between 0 and 8. So you see, depending on the choice you make for alpha, you can find for the expectation value anything between 0 and 8. And of course, this is not acceptable. You should, the quantum physics, the rules, the principles that you apply, the rules that you apply to define quantum states should give you a prescription to decide which value of alpha you should take. And what quantum physics tells us that there are only two possibilities. For bosons, you take alpha equals 0, that is, the state has to be symmetrical. And for fermions, you choose alpha equal pi, which is that these two states should be, this state should be antisymmetrical by exchange of the particle. So you see that now what went down to a complicated calculation of entropy in pre-quantum age became very simple in quantum physics. Identical particles are either bosons or fermions. For bosons, the system should be symmetrical by exchange of two particles, any two particles. And for fermions, it should be antisymmetrical by exchange of two particles. If you assume this, then you have no ambiguity anymore because you have made a very specific choice for the initial state of any system, and then system will evolve without ambiguity. So on the next slide, I give a few examples of what's going on. Let's describe again this problem. Assume that two particles are going towards each other head-on, they interact, and then they leave in another direction. And you want to compute the final state of this. And you find that the initial state that you have to consider is the state that I have written here, pi minus pi plus epsilon minus pi. Epsilon takes the value +1 for bosons, -1 for fermions. So let's look at what happens. What are these two amplitudes? What you can have either, you start from pi and minus pi, and pi is deflected in this direction to pf, and minus pi is deflected in this direction. This is one possibility, which is given by, if you call u the unitary operator which describes the evolution of the system, this is the amplitude of this process is given by this matrix element. And you can have also this process by which pi goes to minus pf and minus pi go to pf. The final state, you see, if you cannot distinguish between these two processes. For bosons, you will add these two amplitudes with a plus sign, and for fermions, we will add them with a minus sign. So you see that you will get very different results whether you have bosons or fermions. And in particular for fermions, it's very interesting because if you look at the scattering at right angle, the probability to go like this, like that, these two amplitudes are obviously equal. And if you have a minus sign between the two, it means 0. Otherwise, it means that two fermions cannot be scattered at right angle because of the minus sign of this antisymmetrization process. So you see that the scattering of boson and fermion take very different properties. There is another extreme case that I show you at the bottom of the slide. In fact, and we'll see that later when we discuss collision between cold atoms. If the atoms are very cold, and what happens is that the wavelengths, the de Broglie wavelengths become very large. And when the de Broglie wavelengths becomes much bigger than the distance over which the interaction takes place, then the theory shows that the outgoing wave is an S wave. It's a wave which has the same amplitude in all directions. In this case, if you have fermions, the final state will cancel because you cannot have two fermions in the same S wave, two electrons in the same S wave. So it means that very cold fermions, in fact, don't interact. They just cross each other without interacting in collisions. And this will have very important consequences when you want to cool down fermions to get interesting quantum effects. Another consequence that I want to discuss here is what is called the Hund's rule. If you suppose that you have two electrons, for example, in an atom, one electron is a quantum state corresponding to a wave function psi, and the other one in a wave function phi. And the question is, what is the global wave function for the system taking the spins into account? The total wave function of the two electrons should be antisymmetrical. And you have two possibilities. Either the spins are in a symmetrical state, and then the orbital, the position wave function should be antisymmetrical, or the spin is antisymmetrical, and then the orbital part should be symmetrical. And you see that this will have very interesting consequences. We have seen before the break that an antisymmetrical state of two spins corresponds to two spin total equal to 0. And a symmetrical state of two spins corresponds to two spins in a state equal, an S equal to 1 state, okay? So what is the difference between the two? If the spins are, if the spin state is symmetrical, it means that the orbital part has to be antisymmetrical. And what does it mean antisymmetrical? It means that the probability to have the two particles together is 0. Because if you have an antisymmetrical state, and if you look at what is the probability to have the two particles at the same point, obviously it will give you 0. The probability will be null. So in a symmetrical spin state, the particles cannot be close together, which means that they cannot repel themselves too much. And it means that the total energy of the system will be lower because of less repulsion when the two spins are parallel. And so it means that when you have parallel spins, the spins have a tendency to go into different orbits. They cannot be in the same state. And it also means that it explains the properties of ferromagnetism. Why do spins have a tendency to align in a system? It's because in the state in which they are aligned, they repel each other less than in the state where they are not aligned. And in fact, this explains the strength of ferromagnetism. At the beginning, people thought that the magnetism was due to magnetic interaction between spins. But the magnetic interactions are much weaker than the electrostatic interactions. So in fact, ferromagnetism is an electrostatic interaction which is mediated by the Pauli exclusion principle. The fact that spins parallel will have a lower energy than spins which are anti-parallel. So this is a consequence of this antisymmetrization property. The last one that I want to show you here is to go to bosons. And I will consider the following problems. I want to look at the scattering. I have a center which scatters particles, and I want to look at the scattering of bosons. What will be the final state of an impinging boson arriving on a potential like that? And I will assume that I have already n bosons in a given direction with a given momentum. And I will try to compute the amplitude that an n+1 boson will come in the same final state. And you see here, the calculation is very simple. What is the initial state, psi initial? It's, of course, a linear superposition of all the possibilities. The bosons that you add here can be the first one, the second one, the third one, and so on. And so you have n+1 possibilities. And since it has to be completely symmetrical, you have to add all these amplitudes. And if you want to have a normalized wave function, you have to divide by 1/square root of n+1. So this is the initial state, completely symmetrical state of one boson impinging on n bosons already in this final state. Now, what will be the final state? In the final state, there is only one possibility. All the bosons are in the state final, and so the wave function is very simple. Now, I have to compute the amplitude of this process. So I have an evolution operator, whatever it is, and I have to take the matrix to the amplitude between the initial and the final state. So you have 1/square root of n+1 times this n+1 terms, u, and this term here. And you see immediately that you have 1/square root of n+1 times n+1 times the same term. So you have square root of n+1 at the numerator. And you find that the amplitude to scatter an n+1 particle in the final state is square root of n plus 1 time larger than it is for the first particle to come into, for a single particle to come into this final state. So there is an amplification. It's called a stimulated scattering of bosons. If you have already n bosons present, the n plus the additional boson will have a probability n plus 1 time larger to go into this state than the first one. And this reminds stimulated emission. In fact, it's exactly what happens with photons. If you have already n photons and an atom which can emit an n plus 1 photon, it will go into this final state much more easily. So this amplification process for bosons is very important because it plays a very important role in Bose-Einstein condensation. Once you have a condensed phase, the probability to have other bosons to come into this phase becomes larger and larger as the number of already condensed state increases. So you have a kind of avalanche effect, which increases the probability for the bosons to fall into the condensed phase. So this is the result of the symmetrization. On this last slide about this topic, I just want to discuss in general the properties, the classification between fermions and bosons. In fact, all the elementary particles which constitute matter, that is electrons, the quarks, which are the constituents of proton and neutron, are fermions. And they are fermions of spin 1/2. So the constituents of matter are fermions, whereas the particles which transmit the interaction, like the photon, which is a transmitter of electromagnetic interactions, or the particles which play the same role for nuclear forces, the gluons which stick the quarks together, or the hypothetical graviton, which is the transmitter of the gravitational force, all these particles are bosons. So the fundamental classification is fermions as the constituents of matter, bosons as the constituents of the vehicles of interactions. Now, what happens for composite system? Of course, in general, an atom is made of a lot of particles. In an atom, you have protons and nucleons, you have neutrons. The proton is made of 3 quarks, the neutrons are made of 3 quarks, you have the electrons. Do they behave like bosons or fermions? The answer is the parity of the number of fermions. If you have an even number of fermions, it means that when you will exchange the two systems, you will change the sign of the wave function an even number of times. And so an even number of fermions will have a symmetrized wave function in the end. So it will be a boson, a composite boson. On the other hand, if you have an odd number of fermions, it will behave as a fermionic system because you will change an odd number of times the -1 sign. So all depends upon the parity of the number of fermions in the system. Let's take the simplest atom, hydrogen. In hydrogen, you have 1 proton, which is made of 3 quarks, and 1 electron. That makes 4 fermions. 4 fermions is a boson. So hydrogen, atomic hydrogen is a boson. You take helium. In helium, you have 2 proton and 2 neutron and 2 electron. It's again an even number of fermions. Helium-4 is a boson. On the other hand, deuterium, which is the nucleus is made of 1 proton and 1 neutron plus 1 electron. That's 3 fermions. It's a fermion. So you see the parity of the number of fermions decide whether you have a boson or a fermion. And the first observation of Bose-Einstein condensation has been made with alkali atoms. Alkali atoms have an odd number of electrons. It's like hydrogen. Hydrogen, 1 electron, lithium has 3 electrons, and so on. So the first column of the Mendeleev classification is made of atoms which have an odd number of electrons. So if they have an odd number of nucleons, if they are isotopes of an odd number of nucleons, it makes an even number of fermions, and they are bosons. And in fact, rubidium-85, rubidium-87, these isotopes of rubidiums are bosons. And these are the atoms which have been the first one to be condensed by techniques of atomic cooling, which I will describe in a later lecture. Now, what does it have to do with spins? An electron has a spin 1/2. If you have an odd number of fermions, the total spin will be an odd number of time 1/2. It will be an odd and half integer spin. So fermions have half integer spins and bosons have integer spins. And the photon is an example. The photon has spin 1. Circularly polarized photons is either +1 or -1 along its direction of propagation. So there is a connection which can be shown by theoretical arguments between the value of the spin and the fact whether the particle is a boson or a fermion. So this is what I wanted to say about this problem. And now I want to address, and I will do it in very qualitative terms, the last part of the lecture, which is about Dirac's equation, because I think it's very interesting and beautiful to show how just theoretical considerations have led to this very important result. The fact that the spin of the electron, the existence of the positron, all have come from very theoretical considerations by Dirac, which discovered his equation 3 years after Schrodinger. Schrodinger is 1925, Dirac's equation in 1928. The problem of Dirac was to write an equation for a wave function which obey the postulates of relativity, which is not the case of Schrodinger. Schrodinger's equation is not relativistic because it does not deal with time and space on equal footing. It's an equation which is a first derivative in time and a second derivative in space, so it does not conserve the symmetry between space and time, which is the main point of special relativity. So Dirac arrived to the equations I have written here, and I just show it for its beauty and elegance. You see, this equation is much more beautiful than Schrodinger's equation. It's a very symmetrical equation. D mu represents the derivative. There are 4 components in mu, 0, 1, 2, 3. 0 is a derivation with respect to time. 1, 2, 3 a derivation with respect to space. In front of that, you have a coefficient gamma mu, which can take it will be 4 different quantities. And the equation is expressed with only 3 parameters, Planck's constant, the mass of the electron, and the velocity of light. So it's a very simple equation, and psi is, of course, the wave function that you want to compute. It's much more symmetrical and much more beautiful than Schrodinger's equation. In fact, one says that Dirac was driven to that because he has a kind of aesthetic view of physics. He thought that a theory had to be mathematically elegant to be true. And this is a philosophical question. I'm not sure whether it's true or not, but this is what really drove Dirac to this equation. So what can we say about that? First of all, I insist upon the fact that the velocity of light enters here. And this brings us back to the topic of this lecture. I want to, in fact, to emphasize the fact that all the things that we are discovering here have a connection with light, which was absolutely impossible to imagine at the beginning. The fact that light intervenes in formula like E = mc² is something which was absolutely unbelievable before the 20th century. So I will just present here the arguments which have led Dirac to this equation and try to discuss its physical content. What are the requirements that were just guiding Dirac towards it? The first one, I already mentioned, the equation must involve space and time in a symmetrical way with the same order of derivatives, which is not the case of Schrodinger's equation. The second condition is that it should be first order in time, that is first derivative, and of course, first order derivative in space also. Why first order? Because a differential equation to first order is such that if you give the initial wave function, you can follow in time what will happen. So you need only the initial condition to understand how the system will evolve, and this is a condition for the theory to be consistent. If I give you the initial state, and if you know the interaction, you should be able to compute everything. So it should be first order in space and first order in time. For a free electron, it should satisfy, this equation should satisfy this equation which we established in the lecture on relativity. E squared minus p squared c squared should be equal to m squared c to the fourth. This is the this is the norm of the quadrivector E over Cp, which has to be the same for all in all reference frames. So you should have this equation satisfied. This is a second order equation. So you should go from this second order equation to a first order equation. And this is what Dirac succeeded to do. Once you have identified E with a first order time derivative and P with a first order spatial derivative, you should get a differential equation which is linear in time and in spatial derivatives, whose solution is an eigenstate with eigenvalue 0 of the quadratic equation, which I have written above. Now, what are the solutions of this quadratic equation? If you solve for the energy, you find energy equal to plus or minus square root of p squared c squared plus m squared c to the fourth. And so if you look at it as a mathematical, just as a mathematician, you find that you have two kinds of solutions. You have positive energy solutions and you have negative energy solutions. But what is the meaning of negative energy solution? You have to give a physical meaning to these mathematical possible solutions. So what did Dirac do? Dirac started with this quadratic equation, and he said, I want to write it as a product of first order terms. I want to factorize it in this way. And if I factorize it in this way, and if I write that the wave function satisfies that one of these terms is equal to 0, then I will have solved the problem. The problem is that you cannot factorize with ordinary numbers. There are no numbers like alpha and beta that you put in this equation, which will allow you to factorize. What you can do, you can try to develop this product. And of course, if you try to develop this product, you will have not only the p squared c squared term, but you will have cross terms, which would be of the form alpha x alpha y, or alpha x beta, or alpha y beta. You will have all kinds of cross terms. So if you want to cancel the cross terms, it means that the alpha and beta have to satisfy anti-commutation relations, which I have written here. You see the alpha coefficient should satisfy this kind of relation. They should anti-commute. And if I is equal to j, they should give you just 2 times the identity, so that you will get just the square term, but not cross terms. And so you immediately come to the conclusion that the alpha and beta cannot be numbers. Alpha and beta should be matrices. And in fact, they should be 4-dimensional matrices. The lowest order you can get to satisfy all these conditions is to have 4 by 4 matrices. And to have 4 by 4 matrices means that the psi that you will have here, the solution of this equation, should have 4 different terms. The quantum state which satisfies this equation, it will of course satisfy this equation, because if you satisfy this, you multiply by this. If you have 0 here, you will have 0 here too. So if you have alpha and betas, which give you the solution of this factorization, and if you apply this linear combination of alpha and betas to a function psi, you will have found your result, but psi will be acted upon by 4 by 4 matrices, which means that psi will have 4 components. It's called a spinor. It's a generalization of a spin, but instead of having 2 components, you would have 4 components. And it's called the Dirac spinor. And from there on, you find the solution. You find this equation, once you replace E by I h bar d over dt and P by h bar over I d over d x dy and dz, you find this equation. You find d over dt and then the gradient operator, which is the result of P acting on psi. This form is not very beautiful because it does not show symmetrically the time and space. So In fact, Dirac has modified it a little bit. And this is what I show in the next slide. So you define 1 over C d over dt, you call C d0, and d over dxi, dx, dy, dz, you call it di. And then you write it on this form, which is just the same thing written with a different notation. And then to get it even more symmetrical, what he did is to multiply by the matrix beta. So gamma 0 is equal to beta, and the gamma I are just the beta alpha g. So he just multiplied by beta on the left, and then he gets the form which I gave you at the beginning. And from that, you can also find very easily the anti-commutation relation of the gammas. And let you show, I show it here. And what you find is that the anti-commutation rules of the gammas give you twice the tensor of special relativity. G0, 0 is equal to 1. The G1, G2, and G3 are equal to -1. These are the coefficients which give you the matrix of the Lorentz transformation, the matrix that you have for the space-time, Minkowski space-time. So in fact, the gammas obey to the anti-commutation corresponding to the geometry of the space-time, and then you get the very simple form that I gave you before. So in fact, I just want to show you the path which leads to this beautiful equation. What you can find very easily if you do the exercise is that the gammas are 4x4 matrices, which are obtained by combining the identity matrix with Pauli matrices. So you see that if you write gamma 0 is equal to 1 and -1, this is a 2x2 matrix, identity matrix. And the gamma 1, 2, 3 are just obtained by taking sigma Pauli matrices on the off-diagonal elements. Take this, compute the anti-commutator, and you will find that this satisfies exactly the anti-commutation rules which are required to factorize the E square minus P square C squared expression. And you see now that if you write the tensor, the spinor psi as 2 component psi1 and as in the first 2 line and psi2 in the last 2 lines, you can divide it into 2 spinors, 2 spins, two spin components, psi1 and psi2. And what Dirac showed, and I show you here, I demonstrated on this slide, is that if you are at a non-relativistic limit, if the energy is very above, a little bit different from plus mc squared, that is if you have a weakly relativistic electron, then psi1 is much larger than psi2. And you can neglect psi2, and psi1 is the spin of the non-relativistic theory. If, on the other hand, you look at the negative energy states, then it's psi2 which is most important, and psi1 which is small. And this is what I have calculated on this slide, on the right part of the slide. You see the ratio of psi1 over psi2 is equal to V over C, where V is the velocity of the electron. If V over C is small compared to 1, psi1 is much larger than psi2. And if, on the other hand, you look at negative energy state, it's psi2 which is larger than psi1. So we still have to understand what the negative energy states are about. When you look at the spectrum of this equation, you see that the energies that you find, the eigenenergies that you find, are either positive over mc squared or negative below minus mc squared. So the positive energy states are above mc squared, the negative energy states are below minus mc squared, and between plus and minus mc squared, you have a gap of 2 mc squared where you don't have any possible energy. So the big question that Dirac asked himself, what does a negative energy state mean? In fact, what happens if you have an electron here? A positive energy electron is something we understand. It's an electron which has which has a rest mass, so if it doesn't move, it will be just at the bottom. And if it has a kinetic energy on top of that, it will be somewhere in the positive energy band. But if you compare that to what happens with atoms, what prevents a positive energy electron to fall into lower energy states by emitting a photon? What Dirac said is it's not possible because I assume that all the negative energy states are occupied by fermions. And so another electron cannot come there because if he comes there, he would be in a state which is already occupied. So he used the exclusion principle to say the negative energy state he called it the Fermi sea. It's a sea of electrons. The vacuum is full of negative energy electrons, which prevent a positive energy electron to fall there. And so the vacuum, you have to assume that the vacuum is something where all the negative energy states are occupied. So then the next, so you can have a positive electron in the positive energy state. Like that, he will not fall. He will not be able to fall in the negative energy state by emitting a photon. But then Dirac considered the opposite process. Suppose what prevents you from sending, for example, a very energetic gamma photon, which has an energy larger than 2mc², would it be possible to go from this negative energy state into a positive energy state? This is like a photoelectric effect. You take an electron out of the Fermi sea and you promote it to the positive energy state. For that, you need a gamma photon, very energetic, which has an energy larger than 2mc². So what will happen in this case? What will happen is that you will have a positive electron here, and you will have a hole, an absence of negative energy electron in the Fermi sea. But what is an absence of a negative energy? It's a positive energy. If you assume that the vacuum is full of electrons, if you go away from the vacuum, if you suppress a negative energy electron, it is as if you had added a positive energy particle. So a hole in the Fermi sea is a positive energy particle. It's also an absence of negative electrons, so the charge is positive. And so he invented the positron. He said, you can excite from the Fermi sea, extract a negative energy electron, and then you will get a pair, a positive electron, and the absence of a negative electron in the Fermi sea, which is a positron. And so he understood the possibility of creating pairs of particles out of vacuum by disappearance of a gamma photon. So this is quite simple, but there is a problem, is that you have to conserve the energy momentum of the system. And if you try to do the exercise, you will find that if you have a non-relativistic particle, if you are very close to the top here or to the bottom here, you will see that it's not possible because you cannot conserve energy and momentum. But you can do that if you are at proximity of a nucleus. For instance, if a gamma ray falls on a nucleus, the nucleus can take the recoil and you can create a pair of electron-positron. And this is the way 4 years after Dirac, in 1932, Anderson discovered the positron. It was a big success of Dirac's theory. So Dirac's theory not only explained from where the spin was coming, because you need, even for positive energy state, you have two components for the particle, which are the two spin state, and it predicted the existence of the positron. So I will conclude very briefly the importance of Dirac's equation. So it's very interesting because it predicted the electron spin, and it showed that the electron spin is required by relativity. It's an intrinsic relativistic effect. And we will see that, and I will talk about it in a moment, if you add, here I describe Dirac's equation of a free electron. But if you put the electron in an electromagnetic field, the spin will interact with the field. And in fact, what the Dirac equation shows is that the gyromagnetic ratio, the ratio between the angular momentum and the magnetism, is twice as big for spin than it is for the orbital momentum. So in fact, the spin is anomalous in respect to the relationship between the size of the angular momentum and the size of the magnetic moment. I remind you that when we studied Himbert's law, I showed you that an angular momentum, the fact that a charge is rotating, creates a magnetic moment. But the magnetic moment of orbital momentum is twice smaller than this intrinsic magnetic moment of the spin. So this is something which comes from Dirac's equation. The positron is also coming from this equation. If you include now the Coulomb potential in the equation, you get now the relativistic equation for hydrogen, and you get corrections over the spectrum that I showed you at the beginning of the lecture, because the spin of the electron interact with the orbital momentum. These are two magnetic moments which interact, and it gives rise to a small lifting of the degeneracies in the energy levels. So Dirac equation computes the spectrum with what we call the fine structure, which is related to relativistic effects. So it completes the model. In fact, it is even deeper than that. What we have come to, the conclusion we have to come to is that it's impossible to make a theory of a single particle, because we started with a single electron and we found that we can create, that pairs can be created. The number of particles cannot be fixed in a quantum theory, because in a relativistic quantum theory, because relativity says that mass and energy are equivalent, so you can create particles out of, for example, out of gamma rays. And the fact that you have quantum fluctuation in the system explains that the number of particles cannot be fixed. So a theory, a quantum theory, quantum relativistic theory, has to be a theory in which particles can be created and disappear. And this is what happens with the photons. Photons can appear or disappear. The number of photons is not fixed. In general, at low energies, the number of particles of boson of Fermi is fixed because you have not enough energy to create new particles. But if you go in accelerator physics where you have fantastically large energies, then you have the possibility of creating new particles, and this is all what accelerator physics is about. And so, in fact, a real profound theory has to be a field theory, a theory in which the number of particles is not fixed. You can create and see particles disappear. So this is what I wanted to say. I just want to add a note. Dirac equation is not the end. There is, even to Dirac equation, there are small corrections which are due to the quantum fluctuation of the vacuum. In fact, the electron is submitted also to the fact that photons can appear and disappear randomly. These are called vacuum fluctuation of the electromagnetic field, and these fluctuations slightly displace the energy levels predicted by Dirac. It's called the lamp shift, and this was discovered a few years after Dirac's equation, and I will come back to this in later lectures. So the conclusion, first of all, I want to say that I have spoken about the spin, but the spin is a model for the description of a large variety of quantum systems whose quantum state can be described as superposition of two components, only two states. For example, a ground and an excited state of an atom which interacts with light, the magnetic moment of nuclei in nuclear magnetic resonance experiment, two-state qubits in quantum information. For all these systems, the Pauli matrices and the Bloch sphere representation would be very convenient to describe the physics. In the next lecture, I will address another very important issue that I have not discussed so far. It's the notion of entanglement. The fact that if you have two spins, the wave function of the two spins cannot be separated. The wave function of two systems in general cannot be separated as a product, tensor product of two independent systems. You have correlations, and these correlations have very strange non-classical properties. For example, one of these properties is called non-locality, and this is a problem that Einstein studied. In fact, the last problem, quantum problem that Einstein tackled. Einstein did not like at all the fact that two systems can remain correlated at a distance in a way which cannot be explained by classical arguments. And this, I will discuss this question of non-locality next week. So I will, next week lecture will be devoted to explain what is entanglement, try to quantify entanglement in a system, and also discuss this problem of non-locality and try to see if this non-locality can be used to teleport quantum state from one point to another one, eventually to communicate faster than light. And we'll see that, in fact, entanglement is strange, but does not violate causality, and physics still stands on solid grounds, in spite of the fact that entanglement leads to very counterintuitive phenomena. So we'll stop at this point, and the next lecture will be just in a week from now. Thank you.